the U.S. Geological Survey did and has continued to do amazingly important work on a huge variety of topics, groundwater, seismicity. So this particular lecture series is sponsored by the IRIS, which is a, oh my goodness, I won't remember how it actually, here, I have it written down, which is the Incorporated Research Institutions on Seismology, and also the SSA, which is the Seismological Society of America. So we're really lucky that those institutions sponsor this lecture, and usually these lectures will be introduced by my colleague Edmund Mattei, who has now actually retired officially from the museum, but we hope to continue these lectures as long as we can possibly do so. So Dr. Rubenstein got received his Bachelor's of Science degree from UCLA, cum laude, in 2000, and his master's and then PhD from Stanford in 2006. And his current interests include all kinds of things that are related to earthquake hazard, but particularly induced earthquakes. And he will explain to us what induced earthquakes actually are. And as a footnote to that, I will hope that by the time he is brought on board as the new energy secretary in the new presidential administration, the person who's been named to that slot will discover that actually induced seismicity does exist and is a factor in various hazards, or something which apparently is not yet believed. But perhaps if he were here, he'd learn that. Dr. Rubenstein.
Thanks, Ben. Pleasure to be here. So, title of my presentation is Yes, Humans Really Are Causing Earthquakes, and I've said it that way to disabuse you of any notion that this is the earthquake surge that we're seeing in the central United States is natural. It really is a man-made earthquake sequence that frankly seems to be getting worse, not better, despite the fact that we're learning more and more about it. So just the cover pictures that I have here on the left-hand side, you can see, pump jacks. I think it's probably pretty familiar to everybody. This is what you're going to be extracting oil or gas with, and plotted behind it is a cumulative count of magnitude 3 and larger earthquakes in the central United States since 1973. And so you can see basically from 73 to about 2009, it's more or less a line. And so that's basically telling us that the earthquake rate is give or take the same every year, because we're looking at a cumulative count. And then things sort of start turning upwards, and when you get to 2014 and 2015, you're having 400, 500, 600, actually last year there were about 1,000 earthquakes alone, which is far more than we saw in the previous 30 or 40 years. So something very dramatically different is happening. And the capital of these earthquakes is in fact Oklahoma. And so I stole this Photoshop from somebody online, and normally when you think of Oklahoma, you think of tornadoes, but now they have earthquakes too, so it's now the home of the Quake-nado. And so I should say, humans really are causing earthquakes, but probably not in the way you think. It is not Max Zorin planting nuclear bombs in the San Andreas Fault in a view to a kill, nor is it Lex Luthor trying to inject water into the San Andreas Fault in Superman 1. Much to my chagrin as a San Franciscan, these guys are both trying to destroy San Francisco. But interestingly, the Superman 1 plot where he's trying to inject water into the San Andreas Fault is more or less exactly what is occurring right now in the central United States and is what is causing these earthquakes. But I do want you to keep in mind this, but not in the way you think. You probably think it's hydraulic fracturing, and that is not actually the case. And we'll get to an explanation of why that actually is. But first, I want to sort of walk you through man-made earthquakes. It's not actually a new thing. We've been doing this for over a century. The first known induced earthquakes occurred in 1894 in Johannesburg. Johannesburg back then was a gold mining town. Gold mines were throughout the middle of the town, and it was these are a couple photos from gold mines in the area. They were doing what's known as room and pillar mining. It's exactly what it sounds like. You'd excavate a room and just leave some small pillars. And so you started getting collapsed features, and the extrication of this of studying human-caused earthquakes, specifically related to mining. And a dozen years later, actually, the Polish installed a seismic network in the Silesia coal basin to try to understand the seismicity there. So this is, really led to actually a lot of advances in seismology. Now, mining isn't the only source of human-caused earthquakes. Oil extraction has also caused a lot of earthquakes. The first known one that I know of is in Goose Creek, Texas. This is clearly very much a bargain spot. You can see, there's oil derricks everywhere, and it's very, very active oil extraction. And this caused earthquakes up to about magnitude 4. And as far as I know, these are the only earthquakes that ever have been felt in Houston, which is about an hour away. But what is going on here is the extraction of all this oil left these giant caverns, sort of causing the same sort of earthquakes that we were seeing from the mining-induced. Now, the last historical kind of earthquakes that I want to mention are reservoir-induced earthquakes, and these were discovered in the early 1930s with the filling of Lake Mead. Basically, by piling on a whole bunch of water, you've added a whole lot of mass, and you're pressing down on faults nearby, and also the fluid may actually sort of leak into some faults. And so this only caused earthquakes on the order of magnitude 3 or so. It did alarm a lot of people, but the earthquakes did eventually go away. But so you can see there are many different kinds of human-caused earthquakes, and these go back many, many years. This is just a photo that's actually fairly recent, and it shows the effect of the drought having lowered the level of Lake Mead. But so let's think about what are the characteristics of induced earthquakes. When I start seeing an earthquake sequence, what are the questions I ask myself? Could this be induced? And really the first questions I ask are these earthquakes close to something that we've done? We're not missing any magnitude 3 earthquakes, despite the fact that we have improved our monitoring capabilities over the years. We should have, even in 1973, we should have been recording all of the magnitude 3s. And you can see the earthquake rate, again, has dramatically increased. And from, we've projected the total number of earthquakes in 2016 to be here based on earthquakes through a couple of days ago. So you can see we've dropped relative to 2015, but still the Central U.S. has seen, we'll see probably somewhere on the order 700 magnitude 3 earthquakes, so quite a lot. And frankly, as far as I'm concerned, I think probably most of the people in Oklahoma are concerned an unacceptable number. And it's not just magnitude 3s; we're seeing damaging earthquakes. And these are just a couple of shots of the sort of the larger earthquakes at the start of the surge of seismicity that we started experiencing in 2009. On the left-hand side is a picture from a magnitude 5.3 earthquake in Trinidad, Colorado. This is an area that I studied pretty extensively for a couple of years. And it's wastewater disposal, which we'll talk about in a little bit, that is believed to be causing the earthquakes in the area. It didn't cause very much damage, but fortunately. It occurred in a fairly unpopulated, lowly populated area. And this other picture is a picture from the magnitude 5.7 Prague earthquake. That is actually how they say it in Oklahoma. Again, it caused a mild amount of damage. It isn't a very densely populated area, but 14 buildings were condemned, and there were a couple of injuries. So it's starting to have some real impact. And this is really the start of the surge of seismicity. And so this seismicity really represents a change in earthquake behavior in the central United States. So plotted on the left are earthquakes for 36 years, 1973 to 2008, again, all magnitude 3 and larger. And on the right, 2009 till last month. And you can see these look very, very different. Here there's earthquakes sort of scattered all over the place. Here you can see there's a lot of dots right here in central Oklahoma and a couple spots here in Texas. But it's not nearly as scattershot as we see here throughout the central United States. And if we dive in a little bit deeper, in this 36-year period, we saw 852 magnitude 3 earthquakes, about 24 earthquakes per year. Obviously, there's going to be fluctuation given aftershock sequences and things like that. And if we look at just the past 7 years, there were actually 2,700 earthquakes in just the past 7 years. So nearly 3 times as many earthquakes in a period that is only 7 years as opposed to 36. And so this is an average earthquake rate of 355 per year just these past few years. But again, remember just last year we saw over 1,000, so the earthquake rate really is increasing. And you know, as you can see here, the earthquake rate here is really concentrated in Oklahoma, but it's, you know, the rest of the seismicity, not just Oklahoma, that's the seismicity. So what I want to do now is sort of show you where the seismicity is really concentrated. So what we have here on the left is a cumulative count of magnitude 3 earthquakes. And what I'm going to do is sort of slowly circle some areas and subtract out the seismicity. So, you know, I've mentioned Oklahoma a couple times. It's really ground zero. So if we just subtract out the seismicity in Oklahoma, this line almost flattens out right away. You know, you're almost more or less at a line. You've removed almost all of this curve. And then if you take away the Raton Basin down here in southern Colorado, northern New Mexico, you flattened it out a little bit more. Central Arkansas, flatter. And then you take away a number of spots of seismicity in Texas, and you're pretty much back to a flat line. All of these areas are very well known for having very strong oil and gas operations in the area. So if you take out of these areas, the seismicity that we're seeing in the central United States is more or less average. The earthquake rate we're seeing is pretty average, and it's pretty scattered like we were seeing in the previous years. So next I want to talk a little bit about Oklahoma, because clearly it is the problem child. And Oklahoma is now ahead of California as of 2014 in the number of earthquakes that they're having. Again, we're looking at a plot of earthquakes up till, I think, a few days ago, of magnitude 3 and larger earthquakes. And shown here in red is the number of earthquakes per year in Oklahoma, going back to 1990, and the number of earthquakes in California for that same time period. And you can see California sort of is averaging somewhere between 250 and 400 per year. You get these big spikes here in a few different years. And look at 2014, it's now ahead of California. It's at about 600. Last year, there were nearly 900 earthquakes, and they're on pace for about 700 this year. So well ahead of what we're looking at in California. As a Californian, I can't say I'm too upset about this, actually. And I should point out again, you know, it's not just magnitude 3s. Magnitude 3s are mostly a nuisance. You're probably not going to see damage. And yet, in fact, just this year, things have really changed in Oklahoma. While the earthquake rate appears to have dropped, the number of moderate earthquakes, and so what I mean by moderate earthquakes, which are magnitude 4, magnitude 5 earthquakes, has actually spiked. We've seen 3 magnitude 5 earthquakes in just the past year, including 2 in the last 2 months, which has made my life pretty difficult. The first was a magnitude 5.1 earthquake near Fairview, right here, and it caused a little bit of damage, not a whole lot of damage. Again, most of these earthquakes are not happening in densely populated areas, so the damage profile really hasn't been that bad. Next was a magnitude 5.8 Pawnee earthquake. Again, it caused some damage. Now we're looking at more significant damage, but it's pretty much all, it's nearly all cosmetic damage. You're not seeing significant structural damage in many of these earthquakes. And this now is the largest earthquake that we know of that's caused by fluid injection of all time. And the last earthquake was the magnitude 5.0 Cushing earthquake that just happened Sunday evening, which kind of inconvenienced me for the rest of the night. And you can see it caused a little bit of damage. There was some structural damage. Most of the photos that you see, again, are really cosmetic damage. So next, what I want to show you is an animation of the seismicity in Oklahoma that really shows you how the seismicity has changed in Oklahoma. And actually, I just got this animation yesterday, and when I was visiting Lamont Doherty over in Palisades, and this will probably be part of the Seismodome next week. So you're getting a bit of a preview. And so what this video is going to show you is earthquakes are going to pop up. It's going to be really boring at first. It's not happening. Earthquakes are going to pop up with little circles. The shading is relative to depth. And what you're going to see is over time, you're going to get more and more earthquakes, and it's just going to be a constant rattle of seismicity. The size of the earthquakes is going to be shown in the size of the circle. So I'm just going to let this go and on. And this is what people in Oklahoma are really living with. And you can really see sort of the evolution of the seismicity, where it really started down here, sort of near the Oklahoma City area. And then in about 2013, 2014, they started exploiting what's known as the Hutton Dewatering Formation, as well as the Mississippi Line. And that's where you started seeing this rapid ramp up of seismicity in late 2014 and 2015. So why is it that we wouldn't have earthquakes in Oklahoma? Don't you need faults to have earthquakes? Well, in fact, the earth is littered with faults. There are faults everywhere. And so this is just a preliminary fault map that was put out by the Oklahoma Geological Survey. They actually put this together with the help of industry. And basically, industry turned over a lot of information that they had developed over the years looking for oil. They were obviously going to be mapping faults, because faults are actually very useful for them to track oil and gas and things like that. So you can see there's faults just about everywhere. And I should say that this is undoubtedly far from complete. The last two earthquakes that we've seen, the last two magnitude 5 earthquakes that we've seen, both occurred on faults that we did not know about until the seismicity started in the area. So there's faults. And the next thing I want to talk about is that magnitude 5 earthquake that just occurred this past weekend. And this occurred in Cushing, Oklahoma. You can see it is the pipeline crossroads of the world. And I went out there and visited in June of this year, and it is an incredibly impressive area. There are 9 major pipelines going. Now, the first oil and gas operation that everybody's going to think about is hydraulic fracturing. This is a shot of a frac job in Pennsylvania. I believe you can see it's an incredibly complex operation. Having visited a couple of frac jobs, I have to say it is a really impressive thing that is going on there. And these frac jobs are done, run for a day or maybe a week, and they pick it up and move to another site. It is really a really impressive operation. Hydraulic fracturing does cause earthquakes. I'm not going to tell you that it doesn't. It's very clearly been connected to earthquakes of magnitude 3 to 3.5. There's some evidence that an earthquake as big as magnitude 4.6 in northern Alberta was caused by hydraulic fracturing, but there's yet to be a study published in the scientific literature. So we're still waiting to fully understand what's happening there. Oil production, so oil extraction, has certainly been linked to earthquakes as well. By the extracting, you're creating these large voids, and it's caused earthquakes as large as about magnitude 7. There was a series of 3 magnitude 7 earthquakes in the late 70s and 1980s in what's known as the Gozli natural gas field in Uzbekistan. Unfortunately, we don't have a lot of information about it, because this was at the time when it was closed to the west, so there's not a lot of information about it. The next oil and gas operation that's been linked to earthquakes is what's known as wastewater disposal, and we'll talk about this a little bit more. It's been linked to, actually this is out of date since the Pawnee earthquake happened, it's been linked to earthquakes of magnitude 5.8. You can see it's not exactly a technologically complex operation. You're dumping water down a hole in a lot of these. This is just another shot of a wastewater disposal well that I visited in Will County, which is north of Denver. And the last oil and gas operation that can cause earthquakes is what's known as enhanced oil recovery, and cause earthquakes about as large as a magnitude 4.5. Now, enhanced oil recovery is what you're doing in enhanced oil recovery is you're trying to enhance your oil recovery in a reservoir. Basically, once you've depleted a reservoir somewhat, it's harder to get the oil and gas out. So what you'll do is actually take some of your production wells, some of your extraction wells, and start flushing water into this reservoir, with the idea of raising the fluid pressure up so it's easier to extract, and also to push the oil towards your other wells that are extracting. It's a very common practice going back to the 1920s in Los Angeles. So how do all of these operations cause earthquakes? And these are the same ways all the other operations that we discussed at the very beginning, mining and reservoir filling, for example, they cause earthquakes in one of 2 ways. One is a change in solid stress or poroelastic stresses, either by adding mass or reducing mass. You're changing how much the earth is pressing down. And so if you have a fault underneath it, you could, depending on the orientation of the fault, the stress by adding some of these fluids could encourage there to be slip on this fault, or it could discourage it. But this is sort of one of the modes that we expect this to be occurring. So that's what's going to be occurring in reservoir-induced earthquakes. It's what's going to be happening in oil extraction-related earthquakes. It's what's going to be happening in mining-related earthquakes. But what we really think is the problem is really fluid injection. And so this is the way hydraulic fracturing and wastewater disposal will cause earthquakes. And that's the fluid pressure effect. Basically, you've got some well that you've drilled here, and you start injecting into some reservoir. It's generally going to be very permeable, and well, most of the time you put the water in, it goes away, you never hear from it again. Every once in a while, though, there's fluid connectivity to a fault. And the fluid gets to the fault and starts prying it open. You've raised the fluid pressure. And so it makes it so there's a little less resistance to slip. It reduces your frictional resistance, and so it makes it more likely to have an earthquake. You could imagine it as more or less lubricating the fault, so making it a little bit more likely to happen. And so this is what we think is really causing the spate of earthquakes that we're seeing, is that this fluid injection is reducing the friction on many of these faults. So I'll walk you through now hydraulic fracturing and wastewater disposal and sort of see as we go through this why fracturing is not new. It is in fact 70 years old. It was invented in 1947 in a Hugoton field in Kansas, and in some senses intentionally making earthquakes. It's intentionally making very small earthquakes, magnitude -2 to magnitude 1. You're trying to bust up the rock by flushing in water at very high pressure, and you're trying to bust up the rock to improve your permeability so you can access more oil. So this is what you might imagine a frac job before. This is the oil that you can access. And after you've flushed in the water at very high pressure to break up the rock, you're able to access that much more oil. So it's to improve the economics of an individual well. And this is just another image of what a frac job might look like when you've got a horizontal well. You can see all of these fractures, so you're able to access more oil or gas. These are very typically short duration. These are going to be done for a few hours or maybe a few days. And you're injecting maybe 60,000 barrels a well in an average well. And the last point, there's no such thing as hydraulic fracturing wells. These are production wells. You've injected the water and then you suck it back out because you want to start extracting oil and gas. So the other kind of well that appears to be a problem and really is the main problem is wastewater disposal wells. But before we talk about wastewater disposal wells, I should probably tell you what is wastewater. And wastewater is any waste fluid that's produced in oil and gas operations. Most of it is what's known as co-produced water. Now, oil and gas is basically the decomposed biological components of relics ocean. And so the decomposition of this means you're going to have oil and the leftover salt water. And so you're going to have oil and salt water commingled. So if you look in this area here, you see oil sitting on top of what's salt water here. And so when you extract oil, salt water comes with it. It's not a choice. And depending on the field, that can be very, very little salt water, and in some fields it's almost all salt water, and it's highly dependent on an individual field. But you're getting this salt water out, and it's typically very, very salty, far saltier than the ocean. So cleaning it up is often not really a practical. And this co-produced water is 95% of the water that's being injected in Oklahoma, for example. In a couple of places, frac fluids actually are the main source of water being injected, but that's a pretty rare case, Ohio being actually one of them. So what needs to be done most of the time, especially when you're dealing with this incredibly salty water, is you need to get rid of it. And the most economical solution that's been come up with is drilling a deep well and injecting into a sandstone or some other porous formation. So here's your oil and gas well. You're extracting your oil, and then you're taking your salt water, your produced water away, and injecting it into some deeper well. These are wells that are going to be operating for years or even decades. You can be injecting up to 1 million, even the biggest wells I've seen are 2 million barrels a month. I mean, an incredible amount of water that's going down these wells. And there's about 35,000 of these in the United States. And very few have been connected to filter earthquakes, but really that number is starting to go. So let's sort of compare hydraulic fracturing to wastewater injection, and what we'll sort of take away from this is that wastewater injection is much more likely to be causing these earthquakes. First off, wastewater injection is a very long-term process. They're operating for years or decades, as opposed to frac jobs, which are hours or days. Wastewater injection is very high volume. You're injecting, millions or maybe even 1 billion barrels in any individual well. And frac jobs are going to be pretty low volume, maybe 100,000 barrels for a big well. So for wastewater disposal, you're putting in way more water, and it's going to be there for a much longer period of time. So you're going to be affecting a larger area over a longer period of time. So the likelihood that you're going to push some fault over the edge is going to be much higher than it would be for a hydraulic fracturing well. And that's actually borne out in our observations. There are many, many belt earthquakes associated with wastewater disposal, whereas hydraulic fracturing has very few belt earthquakes. It's also been associated with damaging earthquakes, while hydraulic fracturing has not. And this is in spite of the fact that there are far fewer wastewater disposal wells than frac jobs. Now, I've told you that these are not new technologies. So what is it that has changed? And it's drilling technology that has changed. In the past 10 or 15 years, drilling technology has advanced in that they're now able to steer wells very well. So what we're looking at now is sort of so now I want to briefly walk through a couple of observations, the classic observations of injection-induced earthquakes. The first were earthquakes beginning in 1962. They were being called Denver. And what was going on is at the Rocky Mountain Arsenal just outside of Denver, they were producing chemical weapons, and there was a lot of gas that had to be gotten rid of it. So they were injected, they drilled a deep well and started flushing it down the well. And it took a few months, but they were able to figure out that when you put water down the well, you started seeing earthquakes. And so what we see here is a count of earthquakes per month, and then millions of gallons of fluid injected per month. And you can see that the injection goes up, the earthquakes go up. Injection goes down, the earthquakes go down. And in fact, they turned off the well for over a year, and the seismicity dropped. They turned the well back on, and the earthquakes came back. An important thing to take away from this, though, and so they shut the well down in 1965 because they realized, they had to stop making earthquakes. And the important thing to take away from this is the biggest earthquake that was actually induced by this fluid injection occurred over 1 year after they stopped injecting. So stopping injection is not a silver bullet. You can wind up with big earthquakes afterwards. And this is just a photo of some damage from that earthquake sequence. So the other sort of classic study was done by a few scientists actually out of my office in USGS in the 1970s. These two gentlemen convinced Chevron to give them control of part of an oil field in western Colorado. And they had a theory that basically fluid pressure is what controls the earthquakes, like what I was telling you. And so what they said is, all right, we're going to see if we can turn the earthquakes on and off. And so first, they pumped water in as hard as they could. And with the expectation they produced lots of earthquakes. And then they said, all right, let's extract all this water. Let's return the reservoir back to its native state and see if there's earthquakes. And if there's not, this will demonstrate that, in fact, fluid pressures were causing earthquakes. Well, that's exactly what they were able to see. So they took a 6-month period. So we're looking at a cross-section, so a side cut where this is, down into the earth. These are the 4 injection wells, and these dots are earthquakes. So looking at a 6-month period where they're injecting as hard as they can, you can see this cluster of seismicity right on the wells, and another cluster of seismicity a little further away. Then they sucked all the water out, returned it to its natural state, didn't inject anything, and this is now a year time period, and there's almost no earthquake. So a pretty clear demonstration that it is the fluid pressure that is controlling these earthquakes. So next, I want to take you through a more modern study of seismicity, of induced seismicity. And this is, in my opinion, one of the nicest studies that I've seen of induced earthquakes. And this was a sequence of earthquakes occurring in Azle. This was an exurb of Dallas, about 60 or 70 miles to the west. And so the largest earthquake that occurred there was a magnitude 3.7, I believe, and it got people pretty upset. It was a very short earthquake sequence, just a few months, but the town of Azle, in particular, got pretty fired up, and they went to their local congressman who came to the USGS and asked us to try to understand what was going on. And this earthquake sequence was, you know, it was a learning moment for the USGS, but it was also a learning moment, I think, for regulators and people that deal with this problem, which showed them that the USGS, while we are really good at what we do, fundamentally, we can't do what we do without high-quality data. And as you might expect, our density of seismic networks is not going to be high in places where we don't expect earthquakes. And so in Texas, we did not have many seismometers. And so for the first few weeks, we didn't have any seismometers in the area. The closest seismometer was 100 miles away. And so the quality of our locations was not very good. And so this is a set of locations just using the network that we had out there. This is a spread of 20 miles. Now, what I'm doing, I'm actually cheating. We actually had good stations at this point, but we did the exercise to see what the locations look like without those new stations. So if we relocate those earthquakes with the new stations, you've now collapsed to a 1 or 2 mile trend. So this really is demonstrating that there's a necessity for high quality data to really understand what's going on. So what these scientists did, some colleagues of mine at USGS, as well as other residents at the University in Texas and Dallas, is they wanted to understand how these earthquakes were caused. And they went through obviously this is Texas, there's oil and gas production just about everywhere. But what to do with wastewater disposal? And so first they wanted to test whether or not it was natural seismicity, but Texas basically has no history of natural seismicity in Dallas. So they were pretty much able to rule that out. So the next thing they tested was it lake level changes? And so the earthquakes occurred right here. This is just showing you the lake level in the area. And you can see it is actually, in fact, at its lowest point at the time of the earthquakes. But then they computed what the stresses associated with the lake level changes. And you can see that there's only small changes right immediately under the fall, or under the lake. And the earthquakes are a good few miles away. So we can more or less rule out the lake level changes. And given that the groundwater changes were much, much less, the water table levels were much less than the lake level changes, they were able to rule out that groundwater had anything to do with it as well. So the next question is it oil and gas production? Well, this is a map of all the wells in the area. Hard to figure out which well is going to cause it. If you look at this Google Earth image, you can see, all these pock marks. Those are wellheads. So there's tons and tons of oil and gas production wells. There are also 2 high volume wastewater disposal wells here and here. And these are the earthquakes. And so what they did is numerically model what the effects of both the oil and gas production as well as the injection was. And your earthquakes, the earthquakes are showing you are lying right here. And you've got your 2 injector wells here and here. And nearly the entire stress signature, that's what we're seeing here in these colors, is due to these injection wells. Now, the producers are very, very close to the earthquake, so we can't rule out that they may have had an influence, but we expect that the stresses from the injection well, which are very, very large, were the main cause for these earthquakes. So most studies of induced seismicity have really been limited to site-specific studies where we look at earthquakes in one individual location. And I was part of a study where we said, all right, well, this is all well and good. We can understand any individual site, but maybe we should try to think about these on the whole. Maybe we can learn about the broader problem and see if there's something, some information that we can apply to the whole situation. And so we gathered, this was really spearheaded by a graduate student at the University of Colorado, who's now a postdoc at Stanford. He gathered all the injection information for all the active saltwater disposal wells in the central United States, all 27,000 of them. And I assure you this data is not in clean databases. It was a Herculean effort. And so these are all the individual wells in the area. He also gathered all of the enhanced oil recovery wells that we discussed a little bit before. And, we really wanted to understand the connection between earthquakes and these wells. So this is just a map of all the seismicity in the central United States from 73 to 2014. And he said how many of these earthquakes could be associated with an injection well. So basically what we said is an earthquake can be associated with a well if if the well is operating at the time and it's within 10 miles of that earthquake. And so shown in red are the locations of all of these earthquakes. There's a lot. But really what we're interested in understanding is what are the operational parameters that affect the likelihood of whether or not you're going to have an earthquake. So we made this figure. So now shown are in blue are all the wells that are not associated with earthquakes, and shown in yellow are the wells that are associated. So the two things that people have really thought about most as what's going to control whether a well is going to induce earthquakes is the injection rate, how much water you're putting down any individual time, any individual month, for example, or maybe it's the total amount that you've injected. That's going to control 100,000 barrels here is pretty much flat. There really is no, there really is no change. But things start ramping up here as you increase injection above 100,000 barrels. So when you get here to 1 million barrels a month, you're at 80 or 90% of these wells are potentially inducing earthquakes. And what's shown here just in these red dashed lines is sort of the expectation of just random association. And so if you lie within these red lines, we wouldn't expect there to be any significant connection. So for injection rate, we do see that it does appear that when you get to these really high injection rates, you should expect that you could be inducing earthquakes, or that at these really high rates that you are inducing earthquakes. So we did the same sort of gymnastics trying to understand whether the total injected volume was connected to inducing earthquakes, and it really doesn't appear that that's the case. So total injected volume doesn't appear to be controlling whether or not you're inducing earthquakes, but injection rate does. We also explored a number of other parameters, like the proximity of the basement. These earthquakes are occurring in what's known as crystalline basement. That's really hard rock that's going to, depending on where you are, is going to be 1 mile, 2 miles, maybe even 10 miles deep. And that's where the rock is strong enough to actually produce an earthquake. Up near the surface, we're sitting on sedimentary rocks. They aren't really strong enough to support the stresses that we need to produce earthquakes. And so we expected if you're injecting very close to the basement, you'd be more likely to be inducing earthquakes. But we were unable to find a connection. That's not to say there isn't a connection, but we were unable to find a connection in this very broad study. We also looked at injection pressure, so how hard you're pushing the water down the well. Again, we didn't find a connection. There's multiple reasons that I would expect for this. I'm pretty sure injection pressure is important, but the thing is, in a number of these areas, the injection pressure data is garbage. It's more or less meaningless. They oftentimes just look at the reading once in the month and just write that number. And also, it's injection pressure at the top of the well as opposed to the bottom of the well. And that, again, we really need to know what's happening at the bottom of the well. And lastly, a lot of these wells that you can literally pour the water down the well and it goes in, those are still inducing earthquakes. It's increasing the pressure, nonetheless, you just need to increment the pressure a little bit. So there's a lot of things going on here. And obviously, geologic factors, which we can't really specifically have, are also going to be important. How close you are to faults, what your stress situation is there fluid connectivity from these wells that are injecting to these faults? And these are all things that we can't really statistically examine, but they undoubtedly are important. So what's the upshot of all this? We've seen this massive increase in seismicity, 3 magnitude 5s in Oklahoma just this year, including magnitude 5 next to was arguably the most important oil and gas infrastructure in the United States. It's not all that good, though. We can control induced earthquakes to some degree. We've seen success taken in Rangeley, as well as Paradox Valley in western Colorado, as well as the Montney Trend in Alberta. Forced shutdowns at times have reduced earthquake rates. This is a photo of an injection facility in the middle of Youngstown, Ohio, that cost a magnitude 4. But the shutdown of that well more or less terminated the seismicity within 2 weeks. We've seen reductions near Anthony, Kansas, Greeley, Colorado, and Love County, Oklahoma, that have all had success as well. Very clearly here. So this is what the hazard looked like in essentially the eastern United States without including induced earthquakes, and this is what it looks like when you include induced earthquakes. And the hazard here in central Oklahoma and southern Kansas is now actually comparable in a 1-year perspective to what it is in California. It's a pretty dramatic change. So moving forward, what can we do? Well, like I said, I don't think we're completely in trouble. The high earthquake rates are continuing, but potentially manageable. We haven't seen any large earthquakes yet. And, by large, I'm talking 6.5, 7, but that certainly is a real possibility. We need to be thinking about that. And we need to be especially thinking about that because earthquakes in the central United States are potentially more dangerous than they are for those of us on the West Coast, because we are building and prepared for earthquakes at this time. And, I do think that there's a lot of positivity, actually, in the industry in general is interested in working with government scientists, interested in working with academics, interested in working with the regulators, because earthquakes are bad for business. And so there has been a lot of data sharing, and there has been a lot of cooperation and collaboration, across all of these different disciplines. And so that's really been heartening. But obviously, more data is needed. We need more seismometers because we're not going to be able to understand these earthquakes without having, and also the seismometers don't always want the data. So, but obviously more research is needed. And if you're interested in more information, fortunately, you should all have a copy of this article that I and colleagues put out last year that's meant as a plain English explanation of induced earthquakes. This is our webpage. We try to keep it up to date with our findings on induced seismicity. You can find a lot of our scientific articles about induced seismicity as well. And I'll leave you here with just the images for Incorporated Research Institutions for Seismicity.
My name is Evan Wade. I have a couple questions pertaining to the politics and I guess the science. In terms of politics, when you have earthquakes, who's responsible for paying the damages? And has there been much protest on the related earthquakes? You talk about the regulation freezing. And the other question is that there seems to be a surge of gas production in domestic production. And it seems to be a policy that was enacted maybe several years ago to increase domestic production. And you think this is a conscious policy in order to possibly subvert the ecology a little bit by lowering gas prices as part of the strategic plan, because gas prices and fuel prices have gone down. That's the first question. Next, the science question is that the water that's being derived, that's coming from the site itself, from the aquifers at the site. And it's fresh water being pumped in and becomes salt water during the production process.
Okay. Multiple questions. So, who's legally responsible for the damage from these earthquakes? That is being handled in the court as we speak. It's being litigated both in our court and homeowners, multiple homeowners, and class action suits are suing operators in those areas. Second question was about politics. I'm going to punt on that. USCS, we don't set policy or anything like that.
I think if you clarify that by saying it's a market forces.
Yeah, I can't tell you what politicians' motivations were behind that. As far as the salt water, so the produced water, frac fluid is in fact fresh water, and they inject that in. But the big problem here is what's called produced water, and so this is water that's native to the formation. It's trapped in the formation with the oil and gas, and so it doesn't really have anything to do with hydraulic fracturing. It's water that comes up with the oil. If you didn't frack the well, there'd still be this produced water problem. The big change is with horizontal drilling, you're now able to make a well that wouldn't have been economical in the past. You're able to make it economical because the ratio of oil to water was too low before, but now that you're able to access more, you're able to get enough oil out of it to make it economical.
I have a question about, you showed that picture of all the oil tanks that are in that particular place in Oklahoma. What are these oil companies doing as a contingency plan if those things were damaged and they created these huge oil spills? Is anything being considered? This is like such a huge risk.
I'm sure they're thinking about it. When I visited a few months ago, we spent a lot of time talking with them, trying to learn about what they're doing, and they have set up, their own seismic network in the area to measure ground shaking, and have sort of response plans. And, after this earthquake, all the pipelines were immediately shut down. They inspected every single one. I think all of the tanks were inspected. But if there's a catastrophic failure, I really don't know. I mean, they certainly, they made a point of telling us how well trained their fire department was for this sort of thing. And maybe they'd be able to handle one or two catastrophic failures, but you've got hundreds of stuff sort of thing. But I don't know.
Your focus, of course, is on the United States, but is this question being researched or examined elsewhere in the world?
Yes. So induced seismicity, the United States really is the problem child when it comes to induced seismicity for wastewater in particular. The U.S. has really been the ones that's really pushing forward on conventional oil and gas, which is going after these resources that have very high water to oil ratios. And so that's a big part of why we're seeing this problem here. But certainly there are injection-related earthquakes in a number of other locations. I've been working with the Italian government on this problem. I'm going to Colombia next month to work with them on this problem. It's certainly a problem elsewhere that people are thinking about, but we have it worse because we're a bit ahead of the curve in the technology for extraction and injection.
Thanks for a really nice talk. I recall that there was the large earthquake in China some years ago that flattened a school and a lot of other things.
The official Chinese reports were that it killed 80,000 people, so you can do the math. There are conflicting scientific reports about whether it was induced. There is a reservoir that was built, I believe, 2 years before the earthquake occurred, called the Ziping-Bu Reservoir, but it's actually a pretty small reservoir. In the grand scheme of things, much smaller, orders of magnitude smaller than the Three Gorges Dam. But there's debate within the scientific community. I don't think it's resolved. Interestingly enough, I would actually say, it's worth noting that one of the studies that says it was induced was actually published by Chinese government research. So I thought that was pretty interesting, but I don't think it's resolved.
Hi, I have.
Right.
Wait, oh, that's fine. Hi, it was a splendid presentation. Thank you so much. I have two related questions, and you may not know the answer to the American one, but you'll likely know the international question. One is there international dialogue of a treaty or other regulatory mechanism? And the other is, if you know, is the Arkansas-Oklahoma litigation federal or state in nature, and do they expect, they probably do they expect it to go up through the appellate process and get joined?
So let me answer the second question first. Right now they're in state court. They're in state court. I really don't know. I haven't heard anything about these cases being joined. I really don't know much about what's happening in the court cases. As far as international regulations, I certainly am not aware of it. American regulations are a real rat's nest, actually. So the EPA sets minimum standards, but states can elect to have their own standards. And so 31 states have taken what's called primacy over the regulation. And in fact, most of them have the same exact regulations, the minimum standards that the EPA sets. But others have elected to have more stringent standards. So, in a lot of countries, especially in Europe, for example, oil and gas regulations are much stricter than they are here. So, but as far as I know, there's not really been any discussion of international regulation.
Thank you so much. Appreciate it.
Thank you. If I'm understanding one of the data slides correctly, the strongest correlation that I think you're showing is between the rate of injection and seismic activity. Assuming I'm understanding correctly, is that a consensus view? Is there a significant other view in the world that, no, this is just not right? And then, I guess my bonus question is, what's the state of regulation of, if injection rate is thought to be the cause, I'll put it that way, what's the state of regulation either proposed or on the books that?
Good question. Well, I should admit, partial bias, I was one of the authors on this study. So there is a bit of a debate. Our study showed that I think very compellingly that injection rate, from our data is the critical component. There was a study that actually came out the same exact day by some colleagues of mine at Stanford. They really argued that total injected volume is the biggest player. To some degree, it's a bit of apples and oranges. We're exploring data a little bit differently. We're looking at individual wells. They're lumping all of their wells together, and I think both are valid and important. They're accessing different parts of the data. Frankly, I think all of these, injection pressure not necessarily as much, but I think all three of these and geologic factors are all important. But this is just what our analysis was able to yield. I mean, we thought 100 different ways of how we could analyze this data. Had we analyzed the data the way that Stanford people did, we probably would have come up with their results. So it's never simple in science. I think there's a lot of important factors, but that's sort of statistically looking well by well. The injection rate appears to be what's important. As far as regulations based on rate or total volume.
Yes, thank you for the presentation. Do you have any statistics on the rate of induced earthquakes, let's say in Oklahoma versus other geological formations such as the Marcellus, formations in the Dakotas, the Permian in New Mexico and Texas?
Good question. So let's talk about the Williston Basin of North Dakota. We all know North Dakota is very, very active, and there's lots of saltwater disposal in the area, but there's basically no earthquakes. And so this is a really important question. How do you have big wells and no earthquakes? And a lot of us have pondered that question. There's only one scientific article on it, and he was a bit equivocal as to what he thought was going on. They have wells that are just as big as we've seen in Oklahoma, Texas. So part of the story, I think, is in general they are injecting into shallower formations. In Oklahoma, they're injecting into what's known as the Arbuckle, which is directly on top of the basement. And the basement is where you're actually going to get the earthquake. In general, in North Dakota, you're injecting 1,000, 2,000, 3,000 above the basement. So it's harder for the water to get to the basement, but it's certainly not impossible. So I think that's part of it. It's also possible that maybe the stresses in North Dakota are not large enough that you're able to produce these earthquakes. Perhaps faults are not oriented correctly in that stress regime, or perhaps your faults are so small that you just can't produce the earthquakes. But to some degree, this is just speculation. We don't have the information. But it's a really important one. I do a lot of work in southern Kansas, and in Harper and Sumner counties, there are huge injection wells in far western Harper County, and there are no earthquakes whatsoever.
The Permian?
No, this is in the Mississippi line. So this is
the Permian.
I'm not actually the Permian. There's no earthquakes, pretty much at all. But if you look at the Mississippi line in southern Kansas, you go to western Harper County, huge wells, 500,000 barrels a month, no earthquakes. You go 10, 15 miles away, you have significantly smaller wells, 200,000 barrels a month, and you're probably magnitude 4. So there's a lot going on that we don't know, and it's probably geology.
Can we get time for a few more questions?
Thank you for an excellent talk. There's something that I'm a little bit confused on that maybe you can explain further. The one part of the presentation, and it's about long-term effects. In one part of the presentation, you, I think it was Colorado example, where they put well water in, earthquakes occurred, and they turned it off and went back to normal activity. And then in another part of Oklahoma, you said even after they stopped injecting into the lake, that there was a major earthquake about a year later. So my question is, based on the state of the data, are there any conclusions that can be drawn about long-term effects beyond when, the well was shut down or whatever?
Okay, it sounds like I wasn't entirely clear. So the example is the Rangeley experiment, where there were no earthquakes. The first 6 months they injected this part, and then the next year they sucked everything out, and they returned the reservoir back to its natural state, and there were no earthquakes. But if we look at Rocky Mountain Arsenal, where we saw the biggest earthquake a year after the wells were shut down, the difference is that they didn't suck everything out. They just left it as it was. And so you still have the fluid pressure increase as opposed to it being gone. So that's good. And fundamentally, the long-term fluid pressure is clearly critical. When you've seen earthquakes being induced 2 years, 3 years, 5 years later after injection stopped. And for this Cushing earthquake, injection had been stopped for a year at the time of this magnitude 5 this weekend. So, long term is very important. And
organization, you collect amazing data over long periods of time with consistent methods. That's the basis of science, the basis of policy making. They go to threat, because obviously you didn't have to